So welcome everyone to the ARENA seminar for this week. I am the host. My name is Tyler Gorda. I'm at the TU Darmstadt in Germany. I do high density QCD calculations to constrain neutron star physics, similar to today's speaker. And today's speaker is Dr. Reed Essick, who's a senior postdoctoral fellow at the Perimeter Institute for Theoretical Physics. Reed received his PhD in 2017 at the MIT LIGO lab. And from 2017 to 2021, after that, he was a fellow at the University of Chicago, a KICP fellow. And his work spans many aspects of physics of compact binaries, including gravitational wave detection and characterization, X-ray observations, linear and nonlinear tidal effects, as well as models of the population of merging binaries throughout the universe. And his recent work has focused on application on nonparametric Bayesian inference to constrain the supernuclear equation of state, and how astrophysical observations inform our understanding of ab initio nuclear calculations and terrestrial experiments. So one thing I would like to say before we start the seminar is afterwards, we will be having a meeting in Gathertown. It will be slightly more informal, I suppose, where you can chat with Reed or with each other, network a little bit, things like this. And Reed said that he's fine with people interrupting him if you have questions. So if you have questions in the middle of the talk and you don't want to wait till the end, feel free to unmute, or I'll also be watching the chat to look for raised hands. So without further ado, Reed, we're very interested in your talk, and the floor is yours.
Thanks, Tyler, and thanks everyone for giving me this opportunity. I'm going to focus on some recent papers along the lines of what Tyler mentioned, and hopefully this, more than anything else, will just kind of give ideas that we can chat about after the talk and in the Gathertown about possible new projects to work on and ways we can connect all the different pieces to really understand nuclear astrophysical objects, right? So the title of my talk is kind of cute: Gravitational Laboratories for Nuclear Physics. I mostly have been looking at neutron stars recently. The two things that are really important for neutron stars is strong gravity, so gravitational waves, gravitational lensing, things like that, and nuclear physics. So it's a nice intersection of the two fields. I've broken down my talk into roughly these three parts, and I'm going to try to stay at kind of a high level. I will dive into details at times, but of course, if you don't understand something or you want to know more, as Heather said, please interrupt me, and we'll have chances to chat after the slideshow finishes. So the first thing is, what do we observe? I'm going to run over the basic astrophysical observatory or observables that I use in my inference. In case you don't stare at this type of data set or think about it all the time, I want to make sure that you're not lost when I talk about the different types of observations we have. I'm going to summarize kind of what I would call the cutting edge equation of state constraints from astrophysical observables. This is in a particular framework, as I mentioned. Bayesian nonparametric inference is something that I've been developing with some collaborators over the past few years. And unfortunately, I don't have time to go into all the details of why we think this is the best way to do it. But ask me questions if you have them. We do think that this is a particularly powerful tool. And then lastly, where I'm going to try to spend most of my time is looking at ab initio theory, nuclear theory calculations, nuclear experiments, and then how we can use astrophysical observations in this framework that we've developed to help constrain and tie everything together. Okay, great. Here's a list of key references. This page will reappear, so you don't need to get a screenshot or anything like that. But I just want to call out that yes, I've written a bunch of papers, but I have a bunch of collaborators, some of who are on a call right now, I think. They're all great. This work would not be what it is without them. So in particular, Isaac gave the sort of intro discussion, or led it, that happened for students right before this. So he's led two of these papers, and I'm gonna try to talk about some of his work. But you should ping him as well as any of the other collaborators I have here. They're all very smart people. Very good. Okay, great. So let's start off with, like I said, just a summary of our observables, the astrophysical observables that we're using. And I'm a firm believer in cartoons in talks. If you can explain it in a cartoon, it means that you probably understand the physical intuition pretty well, or at least that's my argument. So in that spirit, I have this very detailed picture of a neutron star here. This arrow is supposed to represent the spin axis, so it's a spinning object. And with excruciating detail, somewhere in the core, I expect there to be some sort of interaction, some sort of effective action that describes the interactions of the degrees of freedom in there, which is this Feynman diagram. And so the idea is that even if you can write down a theory that you think describes nature at these very high densities, very high chemical potentials, baryon chemical potentials, it may be difficult for you to predict the observable consequences of that theory. It just could be a complicated calculation. And so this ends up producing some uncertainty in the actual behavior of neutron stars. So depending on what is going on in the core, you may get different equations of state, or EOSs. So this is the relationship between pressure and density inside the neutron star. That will lead to different mass radius relations or other astrophysical observables. So I have some examples of possible mass radius relations. These all obey causality and thermodynamic stability. Maybe one of them, the one that I've highlighted in purple, is the truth. And the name of the game is, can we use these types of observations, mass and radius, to try to get at nuclear microphysics? So when I'm far from the first person to ever think of this game, it's been going on for quite a while. I'm just going to summarize sort of the main pieces of information that I've fed into my inference so far. Okay, so what's the first thing you can think about? Well, it's an object that has gravity, so mass is probably important. And if you can somehow weigh or figure out the gravitational mass of these pulsars, you can get some information. So the record holders for confident mass measurements come from radio observations of massive pulsars. So the record holder is this J0740. It has a mass of about 2.08, 2.07, but plus or minus 1. That's basically 2.1 times the mass of our sun. And how does this help us? Well, in these mass radius diagrams, the fact that you have seen a star that is an actual star and has a mass of some number, roughly around 2, means that you get to set a lower limit on the maximum mass of the neutron star. So these mass radius curves all have a common feature, that they only go up so far. There is a maximum mass that each equation of state supports. And the idea here is, if I can see and observe confidently a very big mass, then I know that the equation of state must extend into this light blue shaded region. So that would rule out things like this, but all these other ones are still okay. And that's the basic idea behind this. And I've just drawn it as a sharp border here that's actually got some fuzz on it that has to do with measurement uncertainty. And there are more details to how you actually build this analysis, but this is the basic idea. The mass radius curve has to go up high enough into sort of this region. And the maximum mass, or the mass measurements, are giving you a lower bound, not necessarily an upper bound. Okay. So what's the next thing besides mass? Well, maybe the size of the object, so the radius. And again, we're far from the first people to do this, and people have been looking at the neutron, or they've been looking at, sorry, let me start that again. Some of the most recent measurements have been using the NICER telescope. This is mounted on the International Space Station, and it does a really great job of measuring the time of arrival and the energy of individual X-ray photons. So you can build up the energy dependent pulse profile of these pulsars. So the idea is there's going to be some hot emitting spot on the pulsar. You don't really know its shape, but you can fit for that. At the same time, you can measure the spin of the object, and by carefully measuring this pulse profile and accounting for things like self-lensing from general relativity as light is bent around, you can get an inference for the mass and the radius of the object at the same time. Okay, great. What does that look like? That looks like these darker blue orbs or uncertainty ellipses. And the idea here is that if you do this at several mass scales, right, you can measure the radius at several mass scales. You're going to directly map out these curves, right? So that's great. That's sort of the nicer X-ray timing measurement. You can see that, this curve over here that extends up above 2 solar masses, that looks fine if you just look at the masses, but if you also look at the radius, you can rule that guy out. And if you have more and more of these measurements, you expect to do a better and better job. Okay, so the last type of observable that I'm going to talk about is gravitational waves. This is sort of where I come from, so it's near and dear to my heart. And it operates very much like the nicer measurements. You're going to measure what is called the tidal deformability, or this capital lambda, as a function of mass. So you're going to measure two things simultaneously. And actually with the gravitational waves, the systems that we have measured are binaries. So there are two objects in the binary. So for each object, you measure its mass and its tidal deformability. There are certain combinations of those that are better measured than others, but at the end of the day, you're going to try to constrain all those things. And the physical intuition you should have for what lambda means is how squishy the neutron star is. So because it's in a binary, the companion will exert a tidal field. And just like the moon raises tides on the Earth, there will be a corresponding bulge in the neutron star. Lambda measures how big that bulge will be given a particular tidal field. So, how squishy or how deformable the object is. And the constraints you'll get will look something like this. So instead of mass radius, I'm now plotting mass lambda. You can see again, the massive pulsar is sort of, that's the region that's favored. And I've got two greenish blobs here. As I mentioned, you're measuring for a single system, you're going to measure the mass and the tidal deformability of both objects, which actually means that these blobs are correlated in a way that makes it difficult to plot everything in just this two-dimensional projection, but you can account for it in the analysis. That's not a problem at all. All right, so these are the three basic types of astrophysical observables that I'm going to use in my inference. And now I'm going to tell you about sort of using this data, these types of data, that what we can say about the equation of state right now. And again, as I mentioned, we have a particular way that we like to constrain the equation of state with nonparametric Bayesian inference, which is a bunch of fancy words to try to say that we want to build in as few modeling assumptions as possible, and really try to let the data speak as loudly as possible. So all of these papers that I've shown you are written in this nonparametric Bayesian inference formalism. Some of them are just developing it from just the astrophysics side. Some of it, then the bottom three are connecting that to nuclear theory and experiments. But so I want to mention that I don't have time to go into it, but Essick led this paper. It was actually just accepted into PRD, which is great. And this paper really tries to spell out our case for why we think that this is a really good way to go. Like, this is the correct way to do the inference. It has some advantages over other methods that people use. So ask Essick about it or ask me about it at the end of the talk. But I'm going to focus on this other paper that Essick led. And this is sort of the latest and greatest data sets that are publicly available and what our inference has to say about the equation of state, given all that data. So here are the constraints, and these are what I would call theory agnostic. Some people don't like that term, so let me try to explain it a little bit better. The basic idea here is that we do not want to strongly inform our inference based on any particular theory. And it's to the point where all we try to build into our prior is that the equation of state must be causal. The sound speed has to be less than the speed of light. And it has to be thermodynamically stable, meaning the sound speed has to be positive, greater than or equal to 0. That's all we try to build in. There are caveats at exactly how we do this. And again, unfortunately, I don't have time to go into all the details. But the goal here is to try to have an eyes wide open approach that looks at all possible different equation of state phenomenologies or different behaviors, and lets the data pick out which one it likes, instead of accidentally or unintentionally putting in some sort of theory prior. So with this big table, it's in the paper. You can read through all the details. I've just boxed one number as sort of the common reference point that people use, the radius of a 1.4 solar mass neutron star, so what I'll call R 1.4. And the number that we get out of our analysis is 12.5 plus or minus 1. And this is with only astrophysical data, no strong conditioning on nuclear theory, particularly at low densities. We don't even condition on nuclear theory. above like something like a third of nuclear saturation. So this is a very, very intentionally done to be a very agnostic analysis. And this is the number that pops out to you. So there's a little bit of storytelling. If you haven't seen these, I'll run through what data are pushing on our uncertainty in different regions. So we start off in these mass radius diagrams here with the prior, which is the gray shaded region, and it's very broad. It's intentionally very broad. And so this simple shaded region is actually hiding a bunch of different things. There are many different types of equations of state phenomenology, things with phase transitions or phase transition-like behavior, things that might be just purely hadronic. All those stuff are built into the prior. They come for free. But we start off with this big prior. Okay, great. Roughly in chronological order of the observations, we first add the radio pulsars. So these are just the mass measurements, and they typically affect the knowledge of high mass systems or high densities. And they tend to rule out these small radius neutron stars just because the star would be so compact at that point, it couldn't possibly support itself against gravitational collapse. So the fact that you've seen something up here rules out small radii. That's been known for a while. Gravitational waves came along, and this was actually right when I defended my PhD thesis. It was a very exciting time. And what you can see is although the pulsars are perfectly fine with big radii, the gravitational wave data tends to like relatively compact stars. That's what's suggested by the gravitational wave observations. So the gravitational waves limit you up here at big radii, and you can actually see from the light blue to the green, you push down and there's more support here at lower radii. So that's great. The next bit of information you have is the X-ray timing measurements from NICER. And NICER, turns out, for the systems that have been observed so far, is particularly good at putting lower bounds on the radius. So NICER is what limits you down here, and it pushes you from this green to this blue region up here. And that is basically our final, band for what we think the mass radius is. If you read off at mass of 1.4, you'll see that the width here is roughly 2. That's the plus or minus 1 here. And I should also mention this plus or minus 1 is a 90% credible region. It's not 1 sigma. It's a little bit less than 2 sigma. Okay. So the last thing I've pointed out here is this is the additional bit of information that we get from the radius measurement of 0740. This is what Essick's paper was really pushing on. You can see it's mostly informing us at relatively high masses, high densities. And the whole story doesn't change all that much, but this is where that particular measurement is most effective. So the last thing I'm going to mention about sort of current astrophysical observations in this non-parametric inference is we can go after a bunch of different phenomenology. So one of the nice things about the non-parametric inference is that because I haven't assumed a particular functional form for the equation of state, that's what's meant by non-parametric. I'm trying many, many different things, and I didn't have to come up with the particular shapes by myself and write them all down. So I have a machine that will spit out like a gazillion different types of equations of state, and then I can just check them all against the data and make a computer do that for me. So one of the things that is commonly thought about is the possibility of strong phase transitions, or the appearance of either an excited state or some sort of novel form of matter in the core of the neutron star at these very high densities. And oftentimes, a hallmark of that type of behavior is a reduction in pressure support. So the sound speed will drop to be near 0. The pressure will be relatively flat over some region in density, and that oftentimes will produce features like these black curves here in the mass radius diagram. So the radius or the mass, as the mass goes up, the radius stays roughly the same, and then it jogs over to the left to smaller radii as you continue to increase the mass. So what's happening there is when you hit this phase transition, you lose pressure support until you go to a much higher density. At that higher density, the star will start to support itself again, but it will have collapsed to a much more compact state. And so you end up with this typical phenomenology, and we go and we look for this phenomenology. Specifically, we look for multiple stable branches in the mass radius plane. Okay. And so we've done this, and you can quantify the evidence for or against this type of behavior. But I want to focus on a particular statistic that Essick developed, and it's what we call the transition mass. So as you go up this mass radius curve, there's some kink feature here, or some sort of turnover, basically that mass scale where that happens, the largest mass on the first stable branch is what Essick is extracting. And you can get those for all these black curves. They all have some sort of phase transition, multiple stable branch behavior. And then you can contrast that to things like the blue curves, where they all have one stable branch, and you can sort of say what's going on here. So with this transition mass, Essick made this plot. The black is our prior, and you can see that it's definitely not completely flat, but sort of in the region of interest around here between 1 and 2 solar masses, it's pretty flat. So this says that we have a bunch of phase transitions that turn on when the star is in this mass range. The different colored blue here are his 2 posteriors that he made, and they differ in just exactly what data that is included in the analysis and some small differences like that. But they're mostly giving you the same story. So the posteriors are very happy if the transition mass is at low astrophysical mass scale, so relatively low densities. This could still be central densities well above nuclear saturation, but relatively low compared to the stars that we actually see. Or you can actually see there's a little bit of a bump here. It's happy with very big transition masses. So if the phase transition sets in at mass scales above anything that we've seen, then yeah, the data can't constrain that either. So that's where the current inference is saying these are where things like to be. In the middle region, it says no, it's unlikely that there's a strong phase transition in that mass range. This turns out to be a very important mass range. It's where we actually have observations. So it seems to suggest that all the neutron stars that we've ever seen either have all already undergone some sort of phase transition and they all have exotic matter in their core, or none of them do, right? And it doesn't say any, we can't be confident that there is or isn't a phase transition somewhere. We're just saying that it's not setting in the densities where we're actually observing a neutron stars right now. So that's kind of a neat thing that we can get from this astrophysics inference right now. And then, of course, it would be of great interest to compare this to theory predictions, terrestrial experiments. I'll get to some of that later. But I want to stress one more time, this whole type of analysis comes for free in the way we've set up the problem. We don't have to tweak anything to sort of get this type of phenomenology. It just is naturally a byproduct of how we set up the inference. Okay, great. So now I'm going to go into what will hopefully be of the most interest to people in this talk. And it's really comparing these astrophysical observations to ab initio theory calculations of nuclear interactions and terrestrial experiments. So I'm going to start off with this paper, which focuses on sort of the theory side. And then I will go on to the last 2 papers on this list, which talk about a particular accelerator experiment, the PREX experiment that recently came out. So, right. I have been using chiral effective field theory calculations and using those to help constrain the equation of state. There are a couple of reasons why I think EFT is great. I'm a big fan of the EFT approach. That will become very apparent, I'm sure, throughout the rest of the talk. But a couple of reasons why I like it so much. Instead of just giving you one prediction for what the equation of state would be, it will give you a whole band of uncertainty. So the theoretical calculation comes equipped not only with an estimate, but an uncertainty measure on how accurate I think my calculation is. And that is exactly what you want when you're doing this type of data analysis. You want to know how broad your prior should be. How certain are you that this is what the theory is actually going to tell you? But the other thing that EFT comes along with, which is interesting, is a built-in breakdown scale. So some momentum scale above which you expect the theory to not be a great description, just because you've neglected interactions. And you can write down what that breakdown scale would be in your calculation, but there's some confusion about how to map that breakdown scale to a particular density scale in the problem. So it's not immediately clear what density the EFT would break down at, even if you have some idea of the momentum exchange at which it might start to break down. So that begs the question: instead of just trying to compare the EFT to astrophysical data, can we use astrophysical data to learn something about the EFT, in particular, maybe what this breakdown density would be? And so this is what we did in this paper. You can see that these plots at low densities, they're very tight. So these are different EOSs, and they all follow this EFT prior. At higher densities, they're transitioning to this billowy, smoky plume. That is the non-parametric model agnostic part. So we trust EFT at low densities, and then at some point we say, you know what, the theory's not going to break down. I shouldn't trust it, or it is breaking down to some density. I don't want to trust it above that. So I'm going to go to this non-parametric model agnostic approach and try to really let the data speak up there instead of some theory. And so we set up this way to transition between the two, which is great. But then we can also pick the density at which we do this transition. So on the left, I'm stopping at like half saturation. On the right, I've gone up to 2 times saturation, and you can see that EFT uncertainty bands are growing at higher densities. That's what you would expect. But then at some point, I still transition to this non-parametric, completely model agnostic approach up here. So you do this for a whole series of these breakdown densities, and you're going to get a bunch of priors like this. So the light shading region here is where I stop trusting the theory at the smallest density. This is around half saturation. The dark shaded region is something like I've trusted it up to 2 times saturation, and you get sort of this nested set of priors. Okay, great. Let's hit it with the data, and fingers crossed, what happens? Well, from 1,000 feet away, if you're just looking at very high level things, this is beautiful. Everything falls on top of each other. The precise details of where your theory is breaking down are not going to radically change your knowledge. You know, these curves or these posteriors are all pretty much on top of each other. You can still see the same type of storytelling that I was mentioning before, of where the mass measurements from pulsars are important, nicer in gravitational waves. Up here, this is actually causality that's limiting the equation of state up there. The other thing you can see is that the purple line here is the completely non-parametric approach that knows nothing about EFT. And when you condition on EFT at low densities, you recover essentially the same bounds as the completely non-parametric approach at high densities. So this is telling you that, you know, the fact that you have asserted some knowledge down here, it does not strongly affect you up here. We'll come back to that later as well. So this is great. You know, if we say job done, go have a nice dinner and, you know, celebrate. But if you look at this in a little more detail, you can see, okay, down here in particular, there are some differences between the different posteriors. So you might ask the question, can we use this to tell something about this breakdown scale, like which one of these differences is actually preferred by the data? We do this. The way you do this is on the x-axis here, I've plotted that density scale, that breakdown scale. So if on the right side of this plot, I'm trusting EFT at the higher densities than if I stop at the left side of the plot. And the y-axis here is something like a probability. So it's how much the data likes that model. And the fact that this curve goes up and to the right means that as I trust my theory to higher and higher densities, it is better able to predict and reproduce the observed data. So it's a better match to the data. That's good. And this is what you would want if your theory is under control and well behaved. As you trust it to higher and higher densities, it does a better and better job of predicting the data that you actually saw. It means that your theory is good. So this is excellent. But it does beg the question, what if the theory was misbehaving in some way? Would you be able to tell that from this figure? And to explore that, we took this particular chiral EFT calculation, and at a given density scale, we messed it up. And so the 2 different colors here, yellow and green, are based on this gray. So at low densities, they do exactly the same thing as the gray. And then at nuclear saturation, which I picked just because it's a round number, they do something different. So the yellow one gets very soft, the green one gets very stiff. And what you can see then is if you stop trusting the EFT at low densities, you would expect all these to agree. But at high densities, fingers crossed, you should be able to tell them apart because the green and the yellow do something different. Voila, this is what you get, and that's exactly the behavior that you see. So at low densities, if you stop trusting the EFT below nuclear saturation, the green, yellow, and gray are all on top of each other. You can't tell them apart. They're all equally likely to have produced the data that you saw. At high densities, though, they're very different. So indeed, plots like this tell you that, yeah, you can distinguish between these theories with astrophysical data. And the real important thing is that where they start becoming different, if you look down here, is at nuclear saturation, which is exactly where I put in that difference. So this is a good sanity check that says if I see features, it means that I'm able to extract a physical scale from these systems. I can actually tell when this theory would be doing a better job. So that's great. You may have noticed that this is always said, this panel said pulsar plus gravitational waves. So I'm only using those two data in this plot. If you add the nicer, and this is actually only one of the nicer pulsars, the story changes a little bit. So this gray curve, which is a quantum Monte Carlo calculation at next to leading order, instead of plateauing and being flat here, it actually bends back over. And so the statistical evidence that this theory is quote unquote wrong is very weak, but it does suggest that maybe it's not doing as good of a job at higher densities as at least it did at lower densities. One of the other interesting things that come out of these plots is that we considered a separate EFT calculation in the NBPT with a higher order, so N3LO instead of N2LO. This blue thing contains higher order interactions in the EFT. Those tend to be repulsive, so they add pressure support. Bigger pressures means bigger radii, and the nicer data in particular prefers bigger radii. So that's what's happening here, where now the blue is pushed to higher and higher values. In particular, if you trust the blue up to higher densities, nicer is really favoring it here. So this difference between the gray and the blue, which are actual honest to God theory calculations, might be taken as evidence that above nuclear saturation, the N3LO terms become increasingly important. And if you want to model the equation of state up there, you better include those in your theory calculation. But that being said, it should be pretty obvious from just comparing these two, the statistics are still very weak at this point, in that if you just add one more event, which is the difference from the left to the right, all these curves can still move around. And that's completely expected from just the noise properties of these measurements. There's nothing wrong that's going on here. It just means that when you tell these stories, you have to take it as like with a grain of salt. We still need more data before we can really concretely say all these things. Like that is definitely the case. Okay, great. I've been talking about all these things as if you have to pick a density scale at which you stop trusting the theory, and you have to pick that and just tell all your inference that that's what you're going to do. That's it. That's not actually the case. Here's another big table. You can marginalize over that breakdown density scale and let the data tell you itself when the theory stops doing a good job. We have done this in this paper, and the number that you get for our 1.4 is 12.5 plus or minus a little less than 0.1. Or a little less than 1. So this is roughly the same answer that we get when we didn't condition on theory at all. So that tells us that the astrophysical data is perfectly consistent with the theory calculations at low density. We're getting a consistent story out of this whole approach. This is great. It means that things are sort of working. And as we pour on more data, we would expect just the error bars to tighten up. Okay. So in my last 10, 15 minutes, I'm going to focus on these two most recent papers. And so these look at the application of terrestrial experiments, the P-REX collaboration's measurement of the neutron skin of lead-208. And I'll walk us through that and then show you what we get when we apply this in the non-parametric equation state formalism. Okay, so many of you are probably very familiar with this, but as sort of an astrophysicist or a general relativist, this is something that I had to learn, so I like to make sure that everyone knows what these terms are. The neutron skin is a difference in the radius out to which protons and neutrons extend in a nucleus. So particularly for isotopes like lead-208, where there are many more neutrons than protons, the neutrons are not able to crush into the core as easily as the protons do. There's an extra energy cost associated with the imbalance between neutrons and protons in the core of the nucleus. And that means that because you have just more neutrons, they have to extend out to a larger radius, and you get this neutron enrichment in sort of the outer parts of the nucleus. So if you can measure that difference, that's what's called the skin thickness, how thick that difference is. Then that gives you an idea about sort of the energy cost associated with increasing the fraction of neutrons relative to protons in the core, so at the core density. And so unsurprisingly, that energy cost associated with changing the asymmetry between neutrons and protons correlates strongly with what's called the symmetry energy, in particular the density dependence of that, or the slope parameter. So that's this L down here. And so many different theory calculations have gone out and tried to compute what these numbers should be. And you can see that there's a very strong correlation between them. There is some scatter between different theory models. We actually take that scatter into account. So, there's some uncertainty in the theory mapping, just like we had uncertainty in our EFT prediction. We'll have some uncertainty in the theory here, but we can take an R-skin measurement from the lab, which is a derived quantity, but we can map that into an L constraint. And then the hope is that we can come up with an L constraint from the astrophysics in the model agnostic approach and then compare them. So I will mention that there's this paper, this Reed et al., no relation. They looked at the P-Rex measurement. They inferred a relatively large value of L and suggested that this meant that you had to have a big R1.4, particularly bigger than 14 kilometers. I'll show you the papers that I'm talking about here argue that this is actually not a real requirement. Instead, this is coming from the fact that they looked at a particular theory's prediction for how to extrapolate this L to higher densities. And if you don't do that, if you look at this model agnostic approach, this requirement it doesn't appear. Okay, so how do we do this? I've used the word non-parametric quite a bit. As you can guess, what this means is that I don't have a parameter called L in any of my equation of state inference. I don't have a single number that I can read off. So I have to take this arbitrary equation of state that could describe a neutron star and somehow extract this L parameter, these nuclear parameters around saturation density, so I can do a fair comparison. And we do that using a system of equations, which are a good description of nuclear matter around saturation density in terms of the proton fraction, the nuclear energy per particle, the symmetry energy, and then we impose beta equilibrium. So all these different colorful boxes here represent different ways that information is going into the system of equation. So the red thing here, this is the energy density and beta equilibrium. That's what you actually get from neutron star measurements. So that is the constraint that's bringing in the astrophysics. Everything else, the blue here is just well-measured properties of symmetric nuclear matter in the lab. Green is just a measurement of what you expect electrons to be doing theoretically. And so you can put all these things together, feed in one astrophysical observation or one equation state that's consistent with astrophysical observations into the red box. And the only thing that's left is this black, so the symmetry energy. And in fact, we can get both the symmetry energy and some of its derivatives right in the infinitesimal neighborhood around nuclear saturation. And so this is great. What this means is that any equation of state that you feed me, I can plug into these equations, the system of equations, and as long as I believe that around saturation, nuclear matter is mostly described by protons, neutrons, electrons, and actually we've shown that muons don't affect this at all. You can get the symmetry energy, its slope, and its compressibility. So they pop out. So, okay, we have this program. I can now take astrophysical numbers and plop them into these sort of nuclear parameters. That's great. We do that here in this big confusing correlation diagram. And I'm going to walk you through it a little bit. The big thing that jumps out to me, at least, is these green blobs in all the panels. And that is the completely non-parametric, model agnostic, astrophysics informed posterior. So by that, I mean, I'm using the stuff that I talked about from Essick's paper that only looks at astrophysical data, does not strongly condition on nuclear theory or experiment at low densities. And then I'm trying to say, what can the astrophysical data tell me about things around saturation density? So you'll see that it's this big blob. It's much wider than everything else that I've plotted here. That just says that astrophysical observations do not strongly constrain the properties of nuclear matter around the saturation energy. Sorry, is there a question? Okay. So you can actually see these yellow regions sort of beneath the green. That's the prior. So you can see that the astrophysical observations do change things relative to the prior. There is some information there. It's just not that constraining. So that's great. One of the interesting things, though, is that particularly in the one-dimensional distribution for L, the slope parameter, you see that the peak in the prior is different than the peak in the posterior, and the astrophysical data tends to like L's that line up with the black and the blue. Those are theory calculations. That's just kind of the maximum a posteriori line up. But of course, the green is much broader, so it's unsurprising that it's consistent with this thing just because it's so broad. So like I said, I mentioned the black and the blue are different theory calculations that we sort of average over to try to show you, possible systematics in the way each one of those theory calculations goes. They all line up, they're consistent with the green. The pink here is the P-Rex measurement. And what you can see is that it's broad, but the astrophysics only is broader. So there's plenty of overlap between them. And in fact, the P-Rex actually overlaps with these theory calculations at better than 2 sigma. So they're just barely beyond the 1 sigma region, but there's no real tension between those. Okay, great. So what I take this to mean is that astrophysics alone will not be able to strongly constrain properties of nuclear saturation. There is no tension right now between the astrophysics and theory calculations. There's no tension between astrophysics and P-Rex observations. And in fact, I would argue that there's no real tension between the EFT calculations and P-Rex. To put a number to that, the p-value that you would get is something like 10%, 10 or 12%. So that's interesting, but it's not earth-shattering. We would need a more precise measurement of L or R skin to try to see if there's actually something wrong going on there. So this next slide is pushing on that a little bit. What would happen if we had a more precise measurement of R skin? So on the top panel here, this is the current uncertainty. The middle panels here, this is if I had half the uncertainty, same mean, but half the standard deviation of the R skin measurement. And the bottom one is actually, what if I had a perfect R skin measurement? So the only width here is uncertainty from my theoretical mapping between R skin and L. So this would be like, the best we could ever do in a laboratory. And I want you to focus on the green and the red. Those are the non-parametric, not informed by theory at low densities. The green is astro only, the red is astro plus this P-Rex measurement. So what you can see is as I add P-Rex, there is a shift, right? So L goes to higher, this is what P-Rex is telling it to do. So it's following that, there is information that's being added. I'm better able to constrain L when I use P-Rex. In particular down here, there's the L posterior is much tighter when I include P-Rex than when I don't. However, if you look at the projection into the R1.4 planes, you can see that there is some shift. So there is some information that's being teased out, but the shift is much smaller than the statistical uncertainty. And so what that means is that there's enough model freedom here in this non-parametric model agnostic thing that it can accommodate a large value of L and all the R's R1.4 that are preferred astrophysically. Basically, those two variables do not, one does not necessarily make a strong statement about the other. And the reason that's going on is because this particular posterior is non-parametric, it's model agnostic. I've intentionally tried to not build any theory in there. So the statement really is that if more precise terrestrial observations, terrestrial experiments, are going to improve our knowledge about neutron stars, not only do you have to make a more precise measurement in your lab, but you have to have more precise theory calculations, right? So the connection between the nuclear saturation and several times nuclear saturation that you need to do, you have to have a very robust theory calculation to really make that. If you don't have that, if you have this model agnostic approach, then all bets are off. There's really no correlation there. So the other thing I'll mention is that you can see in these plots, this is all real data. Even if you had a perfect measurement of R skin that was centered where P-Rex measured it, what we find is that there's really no need astrophysically to have an R skin or an R1.4 above 14 kilometers. Like it doesn't really change regardless of whether you incorporate P-Rex or not. So the fact that some people find evidence for large R1.4 given large L, that's because they've assumed a particular theory. When you get away from that assumption, that's no longer a requirement. So all those statements really come with the big caveat that it's in a particular theory. If that theory is correct, that's great, but you got to remember that they have that caveat. So I'll just flash this slide since I'm running out of time. The types of evidence plots I was showing you before, we can play those same games again. We do this in this new paper with more EFT calculations. Again, basically the astro-only data is able to tell the difference between things at high densities, not so much at low densities. But if you include nuclear experiments, then you can start telling about the difference between things at low densities, and astrophysical data will tell you the difference about things at high densities, and you can combine these two in this whole nice framework. So this is the dream, and what I would suggest that maybe we can chat about other things to do or ways to move that forward. In my last few minutes, I want to just tease a little bit more about the ideas what might happen if L turned out to be very large, and what that would mean sort of for astrophysical observations. So the way I'm going to get this is I take my big fancy prior that I have, and I'm going to carve it up into different regions in L space. So the green here is just everything that's in the prior. The blue is a roughly theory motivated range for L. So this is what a lot of theoretical calculations or models would predict as reasonable values for L between 30 and 70. And then the purple here is L has to be above 100. And I want to stress this is actually a tighter constraint on L than is actually suggested by P-Rex even at 1 sigma. So this would be a more precise theoretical future measurement. That would actually, this is not what the actual data is. That's different from the purple. Okay, so you can see that things get divided up in this way. Typically the purple here, which is high L, it likes larger sound speeds at low densities. But then when you get above nuclear saturation, roughly, the sound speed balloons out, and that's because really L doesn't tell you anything about the behavior above saturation. Okay, great. When you add the astrophysical data on top of this, the things that I want to mention first is that at high densities, all these different divisions of the prior overlap. They roughly tell you the same story, and yeah, there are some differences, but globally, again, like the knowledge of what's going on at nuclear saturation is not going to be strongly correlated with several times nuclear saturation. But what's also really interesting is that this purple curve, the big L curve, shows a non-monotonic sound speed, right? So the sound speed goes up, then it goes down, and then it goes up again. And that smells a lot like a phase transition. So the evidence for there actually being a phase transition is weak. But if large L's are confirmed experimentally, given the astrophysical data, we can make something that fits it just fine, but it might suggest that there's a phase transition. So I want to say that there are still plenty of curves that don't actually have this non-monotonicity that could match both. It's fine. This L is a more stringent constraint than the actual accelerated data does, but it's something to keep an eye out for. And it does tie nicely back to the thing I mentioned earlier in Isaac's paper, where the astrophysical data is happy to have a phase transition at relatively low mass scales, which would be still above nuclear saturation, but below several times nuclear saturation. And just to show it, if you add the P-Rex data, all it really does is it cuts out some of this very low sound speed region. It actually cuts out some of the very high sound speed region. So P-Rex tells me that, hey, some of the draws in your prior were too crazy, too stiff. So that's great, but all in all, the story is roughly the same. So that's it. This is things to keep a lookout for. I'm going to leave my key references up while we talk about questions and stuff. Thank you so much for giving me this chance to talk. Hopefully it was interesting for you. I definitely love to talk about these things and think about new ways to combine measurements. If you have any questions, I'm happy to answer them now, but I'll also be around in the Gather Town. So thanks, and I'm happy to answer questions.
Thank you very much, Reid, for this very comprehensive yet still very understandable talk. So thank you very much. Do we have any questions? I see two already. I see Will Newton first. Unmute and ask your question.
Hey, yeah, thanks, Reid. That was an awesome talk. My question is to do with the neutron skin L correlation. So the reason that correlation is so tight is because the nuclear models that are being fit have themselves been fit to, for example, mass data. And that fit induces the correlation between L and the other symmetry energy parameters, the magnitude of the symmetry energy, K-sim, and so on. But then you're mapping your core equation of state, where you're extracting JL and K-sim from your non-parametric equation of state. But you are, am I correct in thinking you're allowing the three symmetry energy parameters to range widely, but then mapping to the neutron skin with this correlation, assuming that the values of the magnitude of the symmetry energy in K sim play no role.
Yeah, right. So let me get to the corner plot. You're exactly right. I structure those systems of equations, and I argue that I can go from the arbitrary energy density and beta equilibrium to symmetry energy L and K. And so in this plot, sort of the upper triangle here should be fine. Like, it does not reproduce the masses of known like nuclei that we've measured or anything like that. Like, we're not conditioning on that, but we think that that's fine. And then the point that you're making is basically taking this L and mapping it into the bottom row, our skin, maybe making some additional assumptions about, conditioning on the masses of low mass nuclei and things like that. That's certainly true. And that could be an issue with the theoretical mapping. We do have some uncertainty here in the theoretical mapping, so we're already trying to account for that. But you're absolutely right that there could be something there that we didn't think. Did I interpret your question correctly?
Yeah, absolutely. Yeah. Thank you.
Chun Wen, you can ask your question.
Hi, first of all, it's a very nice talk. It's nice to see that everything's converging. So I have a question, it's maybe splitting here, but you said in your non-parametric equation of say they are generated by Gaussian process, right? And the shape of the Gaussian process, the distribution of it depends on your kernel, right? So my question will be A, what kernel are you using? And B, does your result changes when you say different kernels? I think not, but I just want to ask if you have made that point.
Yeah, so let me get through my gazillion backup slides. Right. So what you're asking about is essentially this. For those of you who don't know, Gaussian processes, you can think about them as just very high dimensional multivariate Gaussian distributions. And the kernel that we're talking about here is essentially a measure of the correlation between the function values at different x points. So the correlation between y at x1 and y at x2 is described by this kernel, which you have to assume. And so we use primarily for these correlations a squared exponential kernel, which looks like this. It's actually stationary in log pressure instead of pressure, but that's kind of a detail. We have other things that come in there, and this is the assumption that we're making about the form that the correlations take when we build our prior. And so what was pointed out is that the different numbers you plug in here for L and the sigma, those matter. And what we do is we try many different sigma and many different L. So we build a prior that is really a sum over many Gaussian processes, each of which has, maybe really big uncertainties and really small correlation length scales, or really big uncertainties and really big correlation length scales, vice versa. We try all those different combinations, give many different types of phenomenology. And so we think that is a good way to go, but it's definitely something that we need to keep in mind. This is an assumption. If you change that assumption, we don't think it really changes anything radically about our analysis, but it might let you better extract or more efficiently compute certain types of behavior, because that they're either more or less prevalent in the prior based on the assumptions you make here. Did that make sense? Did that answer your question?
Yeah, that makes sense. So what you're saying is if you change these sigma and L slightly, your posterior won't change, right? It won't change your conclusion. Is that correct?
Yeah, and essentially it's because we average over many different values. So I don't think I have a good plot of it. Yeah, apologies. What you can do is if you picked just one set of sigma and L and you ran your inference, you would get one posterior. If you picked a different one, how much would it change? If you make some extreme choices for what sigma and L are, it can affect your posterior pretty significantly. But because we're averaging over many different choices, we think that we're going to be robust against that.
Oh, it's a distribution over sigma and L, is that right?
Yes.
Got it. Thank you
Yes.
very much.
Sidu Lin.
Yeah. Okay, so thank you so much for your interesting talk. I also have a question relating to the neutron skin. So can you go back to the page where you are showing the correlation between your neutron skin thickness and the symmetry energy L?
Yeah, sorry, I got so many slides. Okay, here we go.
Yeah, sure.
This one, right?
That linear line, yeah. So I'm just wondering, okay, we see a nice linear line here, but what's the meaning of the slope of this linear line?
Yeah, that's a good question. I don't know. Yeah, that's a good question. I mean, so one thing that I will point out is that there are multiple people have done sort of a fit to this line, and I am showing one from one paper here. In our papers, we used data from, I can't remember exactly what source, but one of the papers that had done a fit, but we redid our own fit. And different people who include different theoretical models will get slightly different relations here. So it'll tilt up and down. And that then, you know, if you measure our skin, you'll get a different L. In particular for large R skins, you know, if you have sort of a different in slope, you know, this could get pushed up and down a reasonable amount. So that's just, as far as my analysis goes, that is a source of theoretical uncertainty that we try to account for. But I don't have any great physical tuition for, you know, what's going on there. Sorry.
Yeah, thanks so much. So actually this is, I don't know, because you know that you mentioned this Reed paper where they infer that by given the P-Rex measurement, they have a very, very large L, right? But by using their model, actually by using their series relativistic mean field model, they also have this kind of a very nice linear line. But okay, but that might be another different linear line, and by using that line, they infer that this L is about 100 MeV. So I'm just wondering, okay, maybe there are several different linear lines, and this linear, the exact shape and the slope of this linear line is somehow affected by the choice of the models. That's something I'm wondering, because right now you see that, given one measurement of the P-Rex, but we have a lot of different L from different models. So I'm just wondering how the slope or the shape of this kind of the linear lines be affected by the choice of the models. Yeah, but of course, this is still maybe need more discussions. Thanks so much. Okay.
Yeah, so one more thing I'll say about that is, you know, a lot of people, they'll say they do a best fit, right? And then like you can just report that best fit line, and that will definitely change when you change the input theory calculations that you use. What we do in our paper is we actually don't model this mapping between R and L from theory as deterministic. So for a given value of L, there's actually a distribution of R that we support. And that's we're trying to say that we don't actually perfectly know what this theoretical mapping is, exactly because of the concerns that you raised. So we're going to actually say for this L, there's some range of R skin that it is consistent with, and then we use that in our analysis to try to build in sampling over this model uncertainty. We have a particular prescription to do it to try to make ourselves robust against the concerns that you raised. It could be improved in the future, but it's definitely something I think everyone's aware of, and we're trying to take into account.
Yeah. Okay. Thanks so much.
Yeah. Sure.
Betty Tsang.
I would like to ask a question that at some point in your talk, you were showing that to distinguish your different models or whatever, you need the higher density data, not the low density, right? Because you said that you can distinguish it much better. Yeah, like here, right? So all your models are the same below 0.7 row zero. Something like that. And then is the higher density, the higher density data, that will give you a better discriminations. Is that what you're trying to say?
Well, yeah, so I would phrase it a little bit differently, but it's basically that. I would say that the high density data can only tell the models apart if you trust them up to high densities.
Okay, so this is the point I want to make about the P-REX. The P-REX data, even if you read the paper, they are data because they're sensitive to the neutron skin. So they're sensitive to about 2/3 of row 0. So that's why it's not surprising that it's not very sensitive to what you're trying to do. And that was also shown by the nicer people that they say they can vary the equation state below row 0. It doesn't really matter. So then the question, the follow-up question is that we actually have data at the high density. So it'd be interesting to do the similar analysis that you have done.
Yeah.
So I'll contact you after this.
Okay, that sounds great.
Are there any other questions? I don't see any other hands at the moment, but feel free to just unmute if you have one or raise your hand. Okay, so I don't see any more questions, so I suggest that we end the discussion here and we can move to GatherTown. And let's thank Reed again for this very nice talk and stimulating discussion.
Thanks, guys.